Now, before continuing the rest of the discussion on language model, we need to recap certain concept on probability, particularly probability distribution and discrete random variables. So what is a discrete random variable? A variable will be considered as discrete random if it describes an event with finite number of possible outcomes and uh, when there is some degree of uncertainty in the event. So if A describes a situation like this, we will be saying that A is a discrete random variable. For example, A can be it will rain tomorrow, A can be the coin flip will show heads, or A can be Virat will retire. So all of them, in all of these cases, A is basically a discrete random variable. So again, recapping, a discrete random variable is a random variable if it has either a finite or a countable number of possible values with certain randomness. So we have already said the randomness here. Basically, a random variable will be called discrete if it has either a finite or a countable number of possible values. Next is a probability distribution. So a probability distribution basically gives the probability of each possible outcome of a random variable. For example, if we consider this as an urn containing some balls, and if we consider there is a probability distribution associated with the urn, then we can actually compute the individual probability or the generation probability of the individual balls from this urn. For example, probability of drawing a red ball is basically can be computed from this urn. Similarly, the probability of drawing a blue ball or an orange ball from the urn can also be computed, given that this urn is basically associated with the probability distribution. So two necessary conditions to for a distribution to be a probability distribution is basically the probability assigned to each possible outcome must be given a value between 0 to 1 because it is a probability, and the sum of the probability across all the outcomes must be 1. So this is basically considering the probability. So considering this, what will be, considering this as the probability distribution, what is the generation probability or drawing probability of the red ball here? So all total there are 20 balls. Out of them, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 balls are red. So considering a simple maximum likelihood estimation, we can say it will be 10 by 20. Probability of blue will be 5 by 20, and probability of orange will be again 5 by 20. Now, all this drawing, as I am saying, is basically considering that they are with replacement. So if I perform or if I consider probability of drawing a red ball, and then if I consider performing a drawing of a blue ball, I'm considering that the red ball after drawing in the first time, I'm replacing it inside the urn again. So considering this, I hope you can say, you can understand that what will be the probability of drawing 3 consecutive orange balls. This will be basically 0.5 into 0.5 into 0.5. This will be 0.5 into 0.5 into 0.5 again. And this will be 0.5 into red is, 0.25. Extremely sorry, all of them will be 0.25, basically 3 times. 0.25 3 times. For this, it will be 0.25 into 0.5 into 0.25 into 0.25. Now, from this concept, that is, they are considered as independent, the individual balls are considered independent while drawing from the urn, and with replacement, we can replicate this if we consider this urn as the document and this individual balls as the terms, and this is the entire thing is basically the document.